Bunch of profound things. Boom, here we are, circular motion. Sorry, guys, if you're watching this video. Okay, so this, because obviously that's a circle. Uniform circular motion for this portion of the question. What else is going on with this thing? Energy. Where's energy? From where to where? From the top of the ramp to where? So you're saying I could do this for energy? In other words, ignoring this chunk here. To save myself some time, I could let us go that route. To save us a little bit of time and a whole ton of writing. That's a really bad idea. That's for reasons that if we started the work and got like 3/4 of the way down the page, you would realize that that's a terrible idea. The beauty of energy is that energy does not care about what? Your path. It just cares about where you start and it cares about where you end. It doesn't care about any of the crazy garbage in between. If thinking ahead to the circular motion portion, what are we going to need here to analyze this using circular motion? Nathan. We need to know V. We need to know how fast the sucker is going. If we stop energy there, we're going to have to do something from here to here. What are we going to have to do from here to here as the car rises again? And how are we going to do that? You have an object that's rising, which we know this is 24 centimeters. So what are we going to have to apply again if we just do energy from here to here? From here to here, we're going to have to do? No, there's no collisions. More energy. Instead of more energy, is there any reason I couldn't handle energy from here to here? Energy doesn't care what the path is. It just cares as you rise and fall and change your speed. Maybe there's work done. This thing's rolling though, so we're assuming friction is tiny. So this from here, what I'm going to color in green, up to there, is the path that we want to analyze using energy. All of the green. No. No. Because the next piece of information says at the top of the loop, the car experiences a force of 2 newtons. We want to go all the way, because we need to know how fast the car is moving at that point. And all of that is just energy. We could go to here, you're right, and Gersel said it. If we went to here, we just have to do energy again. So if I'm doing energy twice, why can't I just do energy once from there to there? And I could have let us stumble upon that, and if we had more time, and this wasn't a short quarter, and I'm already pressed for time, and the page is kind of tiny, if we had whiteboards, I just go for it. But remember, energy is path independent. You just care about where you start, where you end. And so to analyze it in the middle of the loop is the better call. Then what? We have projectile motion at the end. Okay. Sorry? Is it dynamics good? Does the hill deal with dynamics? If we wanted to do dynamics, how would we deal with that? We'd have an angled ramp. We could find the force of gravity on the ramp. We could find the work done as it rises by gravity. Yeah, no, we don't want to do that. So what are we going to have to do for the ramp portion? It's going to be energy again. Energy from where to where? Sorry, from where? What did you originally say, Blake? If you said the bottom of the loop, there's a reason that I'm actually coloring along the track to show us what parts of the track that we actually covered. We've covered from the top of the track to the top of the loop. Now we've got the bottom of the track to the top of the ramp. Yeah, we're totally ignoring what happens here. But because we stopped here, we don't actually know how fast it's going there. If we had done what Blake said before, we said, okay, let's stop here. Then we do energy again. The velocity of the car at this point would have been the same with the velocity of the car at this point because they're at the same height above the bottom of the track. But because we're just going to deal with energy once all the way to this point, to get to the energy here, we're going to have to deal with energy all the way from the top of the loop. So this is where we're going to have to deal with energy. When you've got an object like this, tracing out the path of the object, making sure you're dealing with it the entire length of the way is never a bad idea. I mean, unless you don't want to, in which case, more power to you. Carry it on in your head, but to make sure we've got it all covered is something I'd certainly suggest would be not a terrible idea. So let's do it. What happens first? Sorry? What's the first portion of the question that we're going to deal with here? This energy? Okay, so you want to deal with that first. Energy says energy initial plus work equals energy final. What kind of energy is present at the beginning? Is there any mention of friction? There is mention. It says frictionless.
But isn't there still that 2 newtons force though?
Frictionless, and that's the circular motion problem.
Oh.
That 2 newtons is the normal force at the top of the track.
Oh.
Frictionless means what? No work. So my initial potential energy is going to equal what if I'm going all the way to the top of the loop here? Yeah, my potential energy final plus my kinetic energy at the end. So let's keep plugging this thing in. PEI is going to give me mgh. That's going to equal mgh initial. That's going to equal mgh final plus 1/2 mv squared, v final squared. I can do something here to make my life a little easier. I can cancel out the mass. Why can I cancel out the mass? It's the same and it's where? Sorry, Blake? Because it shows up in all of the terms, I can divide. If I had a plus work here, I couldn't divide by my mass because there's no mass in that work term. But because mass shows up in all of them, I can divide it out. Sorry? No, that's not how you divide things. Okay. That's okay. It's a long time since grade 9. So we've got 9.8 h. That is the initial height. We don't know it. That's what we're trying to find. That's going to equal 9.8. The final height is what? This is 24 centimeters, which is equal to 0.24 meters, because there is 100 centimeters in a meter. So that's going to be 0.24 meters plus 1/2. V final squared. We don't have that. Bom, 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 bom. So is that where we should have started? No, well, it's not bad. We have to do it anyway. We've gotten this far. So we need VF squared. What's the portion of the problem that's going to give us this VF squared? Circular motion. So now let's go and deal with circular motion in the middle here. Circular motion says I've got F net C equals MAC, and I've got A C equals V squared over R. or what are, rather, the forces on my car in that loop at the top while it's hanging there? Fg, I heard someone say from the back, so the force of gravity acting on the car, and the normal force. Both of those are acting in what direction? Downwards, so into the circle. So let's free body diagram this. I've got Fg and I've got Fn. Both of those are acting in. We can call that in that direction, we can call positive. So I'm going to have Fg plus Fn equals mv squared over r. And we can fill this thing in. The car weighs 350 grams. 350 grams is 35 kilos. It's going to be 0.35 times 9.8. Fn we're told is 2. That's going to equal 0.35 v squared over the radius of the loop, which is 12 centimeters, which is 0.12 meters. So, how fast is that car going around that loop? Okay. So that velocity there becomes the final velocity for my energy equation. And it's going to be the initial for this guy over here, absolutely. So now that we've got a velocity here, we can keep going with this. We can square this thing. What's the height of the ramp? Sorry? 0.33 meters. So 33 centimeters. So this is clearly not drawn to scale. Because this is 33 centimeters and this is 24 centimeters. Okay, we can keep going though, because so we've done A, the release height. We know it's 33 centimeters or 0.33 meters off the ground. We want the range R it travels after leaving the ramp. So we're going to have to do 2 pieces to this, because we don't know how fast it's going at the top of the ramp. To get to that point, though, again, is going to be an application of energy. So, application of energy. What energy, if we follow the pink line from here to here, what kind of energy does it, or how much energy, what kind and how much does it have at the beginning? It's moving, so it's got a kinetic, and it's above whatever this is the implicit 0. So it's got some height above the ground. So it's going to, at this point, have potential and kinetic. So PE plus KE. What kind of energy does it have at the end? Again, potential and kinetic. Wouldn't it have been great if I tossed another block here? Because then we could have done energy to here, momentum to here, energy again.
Yeah, but then you have more things to go through.
You're right. This isn't, Ashton's right. This isn't, I don't think this is terribly difficult. You just got to make sure you're thorough, that you deal with everything along the path as it comes. So, what kind of energy does it have? Potential and kinetic. So, potential is mgh initial plus half mv squared initial equals mgh final plus 1/2 mv final squared. Writing it all out every time, as some of us are not in the habit of doing, is useful. I can do what now? cancel out the masses because it shows up in each term on both sides. And now I can just start plugging stuff in. I got 9.8. The initial height is what? It's 0.24 again. Plus 1/2. That V initial, what is it? Yeah, it's this guy here again. That's going to equal 9.8. What's the final height of my car? 0.06 plus 1/2 V final squared. I want the final velocity of the car going up over the ramp. What is it? .32 meters per second. So that is the speed at which it launches off that ramp. Now what? Now this thing becomes a projectile. So, should I redraw that? Yeah, let's redraw it. Just down here to make our life a little bit easier. So this is the situation we've got. Car, top of the ramp. Speed lines are important. Traveling 2.3 meters per second this way. Should have definitely thought that through a little bit better. We're told the angle of the ramp is 30 degrees. So think back all the way to the beginning. How do we deal with an object in projectile motion?
It would be nice if it went long. That would have been a lot. Bring this leverage to the
What do we do? Break the velocity into components. Why is that useful again for projectile motion? Okay, so the horizontal component is going to be constant because there's no acceleration horizontally for an object in projectile motion. The acceleration is only downwards caused by gravity. So, here are my components. This angle right here is what? That is 30 degrees. Obviously, I'm hoping that's obvious. The angle of the velocity is the same as the angle of the ramp. So then this guy here is going to be 2.3 sine 30. This guy's going to be 2.3 cos 30. And I'm breaking this thing up into components x and y. So, as always, let's build the chart. Velocity in the x direction is that 2.3 cos 30. 2.3 cos 30 is what? So 2. Let's go 1.99 what? Okay, let's go 1.999. So then sine 30 is half? So then 2.3 sine 30 is going to be 1.15. Bless you. So Vx is 1.99. Vy is 1.15. The horizontal distance is that range that we're looking for. And we don't know how long it takes to get there. Vy, what do we know?
distance would be
Well, it depends how you want to deal with this. This now is where, how do you want to deal with the object in projectile? Some of you, if I remember back to your tests, liked to attempt car to the top, then the top to the bottom. If you don't like quadratic formula, that's what you do. If you're okay with the quadratic formula, you can just go straight from beginning to end. So you got to decide how you want to deal with that. How many of you want, is there anyone who wants me to go from here to the top and then the top to the bottom? Does anyone want to see that? Hands up if you want to see beginning to end quadratic formula. Hands up if you just don't care. Okay, and then the rest of you who didn't do anything are just scared of committing. So I will show you top to bottom, or top to middle, middle to bottom later. Getting a handle, though, on this procedure that we're going to do is important because it's a lot faster. So if we're going straight from here to here, what is my displacement going to be? It's negative, not 6, negative 0.06. Over the course of the jump, it's going to get displaced. And again, displacement doesn't care about what happens in between. It just cares about your final position, your initial position, and how they're related to each other. So you were initially 6 centimeters up. Finally, you're at 0. So your displacement is going to be that negative 0.6. These negatives are a whole bunch you got hammered in chapter 1. And we've got t we don't know. The beauty, though, is that this is one object moving in space, 2 dimensions, so that these times are equal to each other. So we find this time, it's going to be this time. We find this time, it'll give us the range. So which kinematic equation am I going to use? Flip back to those. Sorry, one more time.
You use the first.
Do I know VF? No, it's going to have an impact speed. We're going all the way to the end of the problem. We have to use this one.
Yeah.
Okay. So at negative 0.06 equals the initial, this is all y stuff. So this is going to be 1.15 t plus 1/2 negative 9.8 t squared. So that's going to give me negative 0.06 equals 1.15 t minus 4.9 t squared, which is going to give me 4.9 t squared minus 1.15 t minus 0.06 equals 0. And I want to find out what values of t satisfy that equation. So I have to factor that thing. The easiest way to do that is to just brute force your way through the factoring. Don't get smart. Like, oh, I wonder if I can find some factors that, you know, I need 2 numbers that multiply to 4.9 times 0.06, and then they add to negative 1.15. You could do it. It's possible. Don't do it. It's dumb. When the numbers are as convoluted as they are. So we have one tool that just lets us pound right through this problem. That tool is the quadratic formula. One of the most useful things that comes out of 10? 11? Math 11? The way Math 11 is currently designed, it's the most useful thing that shows up. So we're going to get that t equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Did I tell you guys that I once made this b squared plus 4ac on the formula sheet and no one corrected me? And then the beauty was they actually used it, b squared plus 4ac, because they thought I was teaching them secret knowledge, and I felt really bad afterwards. It's not. It's b squared minus 4ac. Just stay true to what you've learned. I make mistakes too. So we plug all these values in. B is 1.1. Do I actually have to show all of the plugging in? We cool with that, yourself? We just kind of go from here. So plug it in yourself. Tell me what it is. Well, I got 2 values for t. What are they? Try that again. I also got Ashton, what you got?
Yeah,
0.279 is the positive one I got. What's the negative one, Ashton?
oh, I didn't bother.
Didn't bother with the negative one. Okay, cool. Okay, and then there's going to be a negative answer. We don't want the negative answer. We're going to ignore that bad boy. Yeah, make sure that you're comfortable with going through this and getting 0.279. So then those of us who've got 0.279, what are we going to do with that value? Yeah, that thing just gets plugged back in over here into the x side of things. Because the x component's constant, that's just constant velocity. D equals vt. The range we're trying to find is going to be equal to 1.99 times 0.279 seconds. We get a horizontal range of how far?
0.555.
What's the fourth digit?
2.
Okay, so 555 meters. 55.5 centimeters. So half a meter, more or less. Well, we got that already, but just a little over half a meter. So, as Ashton said, not overly difficult per se, but it can be incredibly overwhelming at the start. You look at this problem and you say, like what? Which is more or less the conversation that was happening in the middle of the class, right at the start, right? You saw this is where we were going. There was nothing that we did was overly difficult. We just applied truths of the universe, the laws of physics, every step of the way. Removing things where we could. Friction meant no work. That's uniform circular motion. Velocity gets used here and here. The fact that there is no acceleration in a horizontal direction for an object in projectile motion. And it just kind of all fell apart. Chapter 1, Chapter 3. The only thing we don't use here is torque. Is why I could bring torque into this? And you probably don't want me to do that.
Put a seesaw in. Oh, that'd be awesome.
That'd be awful. Okay, I could ask for a very particular detail about the seesaw. Yeah, that's true, I suppose. But that'd be hard because you have a moving object on the lever. Its position's constantly changing. You wouldn't be able to do that. You need calculus for it. Okay. Questions about any part of this? It's a lot of work, but nothing I don't think is overly difficult in there. You just have to know. First of all, you have to believe that you can do it, because you all can at this point. You've been exposed to the tools that will allow you to do this. And then just start taking baby steps. There's a hilarious movie called What About Bob? If you're into like cringy 90s comedies starring Bill Murray, go find What About Bob. It's hilarious. It's all about baby steps. And that's what this requires. Not necessarily. Maybe. Lots of questions. I mean, it takes a lot of time.
You know what our exam is?
Yeah. Yeah. No. I have not given. I currently, as it stands right now, your test tomorrow doesn't have anything that gross. Or not tomorrow. Not tomorrow. Your test coming up this week. This is the last lesson. Your test on Friday has nothing that gross on it yet. There's two reasons why I could. You have a fiver with my name on it.
I have 0.0000.
We'll see what happens. As it stands, it's not on there. I've been playing with the idea of tossing one in here that involves momentum. It would be great. Maybe we'll see what happens. Flip the page. Twice.
Will it be something like this on there?
What?
This is like.
But it's everything. That's less a chapter test and more a final exam style of question. It's like it's got everything. Here you go. One question on the final that involves every chapter we've done. Torque is the hard part, though. I don't know how to involve torque in a way that is doable. Okay, a roller coaster. A roller coaster barely makes it around a vertical loop of radius 4. Find the normal force of a 50 or the apparent weight rather of a 50 kilogram passenger when the coaster returns to the bottom of the loop. We know three things. The radius of the loop, the fact that the coaster barely makes it around, and that the mass of the rider is 50 kilos. That's it. That's all we've got. Let's do it. Joseph seems to think that's okay. Well, Joseph's right. That is okay. Otherwise, I wouldn't give you a question like this. Joseph, how do we do it? Where do we start? Okay, Zach, where do we start? No, you said it's okay. You gotta have some clue. Just give me something to like the hardest part of this for the hardest part of this, the hardest part of this for you guys on your own, like as we talk it through, a lot of you are nodding. Like, yeah. And then I throw you a question like, Zach, you were like the previous question. Okay. And I gave you another no. It's like the previous example gave you no tools. Okay? This is completely psychological. And students do this all the time. I see it in math. I see it for obviously the first time in pre-diploma math 9. They just sit there and they stare at a problem. I don't know where to start. Like, well, what have you tried? Nothing. Okay, well, you're screwed now. So, like, literally, especially in physics, just do something. Literally anything is better than just staring at it and trying to figure it out in your head. Figuring it out in your head is the wrong way to do it. Zach, you've said it a couple times now. Where do you want me to start? Why? Do something. Okay, so work energy equation. What portion of the problem is going to deal with work energy? Yeah, we could analyze any part of it. Absolutely. Let's look at what we're given, though, and narrow our focus a little bit. Hold on, no, we're doing Zach's thing. Zach wants energy. He was the first one to speak up. So Zach, where do you want to analyze energy from? Do you know the height? So you can't deal with it from here. Okay? So the question says, let me read the question again. A roller coaster barely makes it around the loop. Find the normal force of a 50 kilogram passenger when the coaster returns to the bottom of the loop. So the only portion of the problem that we actually care about is what? Is the loop. So the energy is going to deal with what portion of this problem? We can't, it's not possible to find that because Zach already outlined we don't know what this height is. We have no idea what the speed of this guy going into the loop is. Let's just make some crap up. No. Okay? No, so we've got our work energy, but we haven't analyzed what part of the problem we're going to deal with work energy. The problem is the way that this thing's drawn is screwing with you, right? What if I did this? We already have established that part of the problem doesn't give us the height. We're not asked to find the height. We can't do anything with it, so that part of the drawing may as well not be present. So Zach, you wanted me to write down energy plus work equals energy final. You probably wanted me to do that because there was the ramp at the beginning, right? But now we've established that the ramp is useless. So is this still useful? Blake, why is energy still useful?
Because you still got to figure out from the top of the loop to the bottom.
Energy is still useful because it's the only tool we have to analyze that. We can't use circular motion for this portion of the loop. because at this portion along the loop, I've got a constantly changing normal force inwards and gravity's acting downwards. Like, I have no way of connecting gravity and normal force. I have no idea what's going on here. But energy is a useful way to acknowledge I was at some height and now I'm not. That potential energy that exists here has to be converted into some speed. So energy is the useful way to analyze that. So you were right to suggest that this is where we start. You were right for entirely the wrong reasons. You saw ramp, you're like, yes, ramp. Ramp means energy. But then we established that No, it wasn't. That was not mocking. That was like, that's your inner monologue. I wasn't trying to mock him. He was like, yes, this is where we're going. This is not where we're going. Okay, sorry, I wasn't trying to mock Zach. So let's keep going with that. What kind of energy is present at the beginning? I have to have kinetic energy. If I don't have kinetic energy, this guy's going to fall. So there has to be kinetic energy at this point here. I'm going to call this my initial state. This is my final state. So I have to have some kinetic energy there. Otherwise, the dude's not making it around that loop.
Does that mean it's not zero?
What does barely makes it around the loop mean? No, that's not what that means. It's not what that means, guys. Barely makes it around the loop. It's not work. The minimum velocity means the normal force is approaching what? 0. So it's here, it's Fn at the top equals 0. That's what the barely makes it around the vertical loop is connected to. The barely escapes the Earth's velocity, or the Earth's, barely escapes the Earth's gravity is PE and KE equals 0. See, these are all the really fine details that the back of your formula sheet would really love to carry for you. It would. It spoke to me. It would. Okay? There's different kinds of, like, we've got a lot going on here. We've got circular motion and we've got gravitation. Being able to identify the language here. Barely makes it around the loop. Fn top equals 0. Escaping to infinity, barely escaping gravitational pull. PE and KE final equals 0. Like, that's the kind of detail that I would definitely toss in the back of a formula sheet. So we've got kinetic energy initial. This thing's above the ground. Let's call this thing the height. So we've also got potential energy at the beginning. There is no mention of friction. This thing's on wheels. So when this thing is on wheels, it's not sliding. Not sliding means we can ignore friction. Because the only friction that's going to exist on this guy here are going to be caused by the bearings inside those wheels. Or if this is a Hot Wheels car, the plastic wheels as it rolls around that little metal axle. We're going to assume it's negligible. So this is going to equal, what kind of energy does this guy have at the end? Only kinetic. If we called this height h equals 0, which is the smart thing to do, it's only got kinetic at the end. So half mv initial squared plus mgh initial equals half mv final squared. I cancel my masses. Let's plug some stuff in. 1/2. Okay, what is my V initial? Doesn't say. Shoot dang. Okay, so we're going to leave that open. Plus 9.8, my initial height. That's a 4-meter radius loop, so my height is 8 meters. That's going to equal 1/2 V final squared. That's what we're looking for. So I want to find the speed at the bottom of the loop. I got to use circular motion. Okay, let's do it. Circular motion, so what part of this circle is going to give me that? the top. Okay, so let's analyze the circle at the top. FNC equals MAC, and we're told that, well, we know for an object in uniform circular motion that the acceleration while it's in the circle is equal to its speed divided by the squared divided by the radius of the circle. So, what forces are acting on the guy in the coaster at the top of the loop? Only FG. Because barely makes it around a vertical loop implies Fn top equals 0. So we're going to have Fg equals mv squared over r. So we're going to have, do we know what Fg is for this person? 50, yeah, so that's going to, I'll just do it this way. Mg equals mv squared over r. Actually, do we even need to know Fg? The beauty of this, because I have no Fn here, my masses can cancel. So I'm going to get that the square root of Rg is going to equal V. That's nice. So how fast is Buddy Guy going? Implication here is it doesn't matter what the mass of the rider is, which is pretty cool. .26 meters per second, and that's going to go in here, the initial velocity for the energy part of the problem. So now we've got that. That allows us to find out the speed at the bottom of the loop. How fast is Buddy Guy going at the bottom of the loop? Thank you. The voice from the back. It is a nice number. Is it exactly 14, Abigail?
It is.
13.9999? Yeah, yeah, we like that.
Exact answer for initial velocity.
Oh, you didn't round this?
No, I
Okay.
didn't round it at all, but I got exactly 14.
No decimals.
No.
If we use the unrounded, that's awesome.
Yeah.
Love that. Okay, so that'll give us the final velocity. That's the velocity at the bottom. What we want is the normal force of a 50 kilogram passenger when the roller coaster returns to the bottom. Because now he's not barely doing anything. He's fully in contact with the track. So he's going to have Fg downwards still and Fn upwards here. I've switched to pink. So let's analyze the bottom of the track. FNC equals MAC. AC equals V squared over R. So how are the forces involved going to give us our net force? Force normal minus force of gravity, thanks Abigail. So we're calling into the circle positive is what you've done. Okay? Fn minus Fg equals mv squared over r. We're looking for Fn. So Fn is going to equal mv squared over r plus Fg, which makes sense. Like this is suggesting that we're going to feel heavier at the bottom because our speed carries us through the bottom of this loop, which makes sense. This is what you've personally experienced, those of us who aren't too scared to go on roller coasters, which was not me until fairly recently in life. Hated roller coasters growing up. Hated. If only we could go to Playland. This velocity here is going to become that velocity there. So Fn is going to equal 50 times 14 squared. The radius of my loop is 4. Plus Fg, which is 50 times 9.8. The Fn experienced, or the apparent weight of our rider, how heavy you feel at the bottom of that loop is what? Thank you, Abigail. 2,980 and 40 newtons. Let's convert that to a mass in kilograms. How do I go to kilograms with this? Divided by 9.8, 300 kilos. And I'm going to call that apparent mass. To give it some context. So a 50 kilogram person is going to feel 300 kilograms coming around the bottom of that loop, which is, yeah, that's so basically the feeling of force of 6 Gs coming around the bottom of that loop.
Isn't that bored of like you're gonna pass out?
That's the tipping point for normal people. 5 or 6 Gs is probably going to knock out a normal person.
It suggests to wear tight clothes for this ride.
It's cool. That's good.
No pregnant people.
Yeah, no pregnant people. Certainly no pregnant people are going on this ride. Yeah, that's not ideal. Yeah, Nathan. Sorry? We're not using G as an acceleration. We're using G as the gravitational field strength. It's a good question, though. That goes back to the Veritasum video I showed you. How can we deal with? Yeah. Good question. There's just things we take on truth. Okay, there it is. That's it. Piece of cake, right?
No.
Like it better than the orbital stuff? Okay, what I want you to work on is this. 1, 2, 4, 5, 8, and 10. Oh, hold on. 3 is good too. We're just going to tweak this here. 3, I like 3. Yeah, so we're just not doing 6, 7, and 9. We'll leave that there. Yeah, we'll call that good. I'm not going to add any more. Okay, so the remainder of class today has already been speculated on by a few people. I have the reviews printed. This is the last lesson out of, I mean, this looks like there's a fair bit more in the book, but that's just extra practice. We give you a sample exam style questions at the back. It's good stuff. Some good stuff in there. At 10:30, I'll come around. I'll hand out the reviews. The rest of the class today, you will have to start those things. Tomorrow, I am going to start electrostatics. Friday, you're going to write me physics test. Unless you can give me a compelling reason to move it. No, you're working on the review today.
Tomorrow, National Day of.
So I'm not hearing anything. The National Day of, think of something fast.
Zachary's
Okay, Garrett,
favorite.
work on this. As always, comments, questions, concerns. If you're done these questions before 10:30 and you want to review, they're sitting at the back table right next to the door. And like I said, tomorrow we start electrostatics. Oh, I'm supposed to nag some grade 12s. Okay.
So you always have it basically pushing it towards the center.
There has to be. If it's traveling on a circular path, there has to be a circular.
Even with that question we deleted that loop, there's still like a tiny amount of normal force going towards the center.
No, it's FG. It's
Or, yeah, but I'm saying if there were a little tiny bit, like 0.00001, it would still be pointing towards the center.
Yeah.
Okay.
because it's on the inside of the loop.
Okay, yeah, okay. I think that's where I had it.
Okay, here we go. Oh boy. I gotta harass a few of you. Ben. The Hound of the Baskervilles. Fantastic Sherlock Holmes story.
Oh, yeah.
Overdue. Needs to go to the library. Mateus. Book going to the library. Kyung Bean. Title going to the or not whatever. You know what book you've got out? You have a library book. It's overdue. Get it in. Nathan Ellis. Get that going on. Get it in there. Who else we got? I mean, I love that you guys are reading. This is great, but we got to return the books at some point. Jaya. Everyone's favorite book for middle school. Used to go back to the library. No, The Outsiders.
Oh.
It's a great book. It's an even better movie. Have you watched the movie, Jaya?
No, I didn't like the movie.
With Tom Cruise? You're very young. Oh, it's so good. So bad, but it's so good. Nesbit. You got a book out too? Yeah. Loki, Where Mischief Lies. Oh wait, hold on. No, I lied. Wrong Nesbit. I was looking at last names. You have two T's, it's one T. Never mind, you didn't take a book out on Loki. Anybody else? Nope, that's it. Okay, you got books. They're due Monday. Get them in, or you're gonna be charged for them if you want to graduate. Sorry?
When we were reading, like, outside of middle school, before we started reading, you basically spoiled everything for us.
So stupid. Why would you do that?
They did it accidentally, but they still did. So, it was like the sheet where it's like, oh, you can answer these questions after reading the book. It was like, oh, this character dies.